I'm afraid I will have to start this course with a topic which doesn't sound very interesting at the first glance, with the principles and physics of ultrasound. I promise I'll try to make it as exciting as possible, and I'm sure that if you really know the physics and principles, you will understand much more about echocardiography. If you don't want to watch this chapter, go ahead. Just skip this chapter and go to the next chapter. I'm sure you'll come back later. Now this creature here certainly has no idea about the physics of ultrasound. It just uses sound waves to navigate. But still, it has to adhere to the limitations and the physics of ultrasound. Did you know that bats really love moths? And moths are actually pretty smart creatures themselves. They use the limitations of ultrasound to disguise themselves so they're not caught and eaten by bats. So what they do is, they try to keep out of the reach of ultrasound, which is approximately 10 feet, at least for bats. And what they do is they can hear the sounds that bats generate and thereby keep at a distance from the bats. In addition, moths generate a clicking sound which confuses the bats. In other words, they're simply producing artifacts for the bats. So, the same principles apply in the nature as they apply in diagnostic ultrasound. So what is the key lesson here? The real masters of ultrasound are not bats, but moths. At least some moths. So first we have to deal with the physics of ultrasound to understand how an ultrasound wave is generated, what the components of a wave are, and how it can help us to generate an ultrasound image. First I would like to describe what a sound wave, and in particular an ultrasound wave, actually is. Basically, what we have is we have regions of compression and decompression, which travels in tissue, for example. To describe the ultrasound wave, we have to look at several features. First of all, at the wavelength, which is nothing else than the distance from one peak to the next. In other words, from one maximal point of compression to the next. And the velocity is the speed with which the sound wave travels through materials. And this speed or this velocity depends very much on which material the sound wave is passing through. For example, for air, we have a velocity of 330 meters per second. In principle, the more dense the material is, the higher the velocity. Note that the velocity is quite high, for example, in metal. And also note that the velocity is quite similar for tissue and blood. Both materials that we're imaging with the help of ultrasound. And the frequency is defined as the number of cycles which pass through a certain point in a certain time interval. It is calculated in cycles per second, the unit is hertz, and as you will see later, it is closely related to the velocity. I'm sure you still all remember physics and the relationship between the wavelength and the frequency. The frequency is inversely related to the wavelength for a given velocity. In other words, the higher the wavelength is, the lower the frequency is. The wavelength is defined as the velocity divided by the frequency. Finally, the last attribute of an ultrasound wave I would like to discuss is the amplitude, which is measured in decibels or in Pascal units. In principle, it is nothing else as the amplitude of the ultrasound wave, and it reflects the degree of compression of the tissue, basically. We'll talk later why the amplitude is also important in diagnostic ultrasound. But coming back to our bats and to why ultrasound works, well, it only works because the ultrasound wave is reflected. And reflection occurs if we have different tissue characteristics. Here, for example, the ray is reflected, and part of the ultrasound wave then penetrates further into the tissue. And this reflection is then used basically to generate the image. So the principle of ultrasound is not only sending a signal, but also receiving the signal. This is also the way a ship is able to determine how deep the water is with the help of a sonar beam. And this is also the principle of radar technology. But let's come back to our tissue example and see how ultrasound can help us to generate an image. Well, we said that we have a reflection if we have a boundary. But in tissue, in reality, we have not only one boundary, but we have multiple boundaries. And part of the ultrasound beam penetrates, so we have multiple reflections. Obviously, these ultrasound reflections will not all return to the transducer at the same time. The further away the reflection occurs, the longer the time until it is again received by the transducer. And by calculating the time it takes for the ultrasound wave to again return to the transducer, and if we know exactly how fast the ultrasound wave travels within the tissue, we can calculate where the point of reflection had occurred, and we can generate an image. This is the principle of diagnostic ultrasound. One final last thing to keep in mind: the ultrasound beam gets weaker and weaker the further it penetrates into the tissue, simply because some of the ultrasound wave is reflected. This is what we also call attenuation. So the physical principle of attenuation sets the limit as to how deep into the body the ultrasound wave can penetrate and where we can still image. The definition again is loss of ultrasound energy due to reflection and scatter. Let me now come back to the reflected ultrasound wave, which is very important to generate an image, as you saw. Well, as you probably again remember from physics, the angle with which an ultrasound wave is reflected from a flat surface depends on the angle with which it hits the surface. So in this case, for example, the ultrasound beam will never come back to the transducer again. So why then do we generate an image? Most of the ultrasound waves will probably hit a surface at least some angle. Such a situation, as you see in this diagram, where the ultrasound beam is oriented exactly perpendicular to the surface and again is reflected in such a way that it is again received by the transducer, is fairly uncommon. The reason why ultrasound still works is because we usually don't have flat surfaces but some texture. And this texture causes the ultrasound rays to scatter in all directions. And thereby we have reflections which do hit the ultrasound beam while others don't. So even if we have an angle towards the surface, at least some reflections will again return to the transducer and help us build an image. So to summarize the characteristics of an ultrasound wave, we will find reflection, scatter, absorption, and penetration. This diagram here should now help you understand which part of the spectrum we are using for diagnostic ultrasound. Not very much, actually. In the very high frequency range, we have cosmic rays, gamma rays, X-rays. Then we come down to the range of visible light, infrared light, radar. And now here is the region where we have sound and ultrasound, and then subsonic ultrasound. This is the scale which corresponds to the low frequencies. We have infrasonic, sonic, in other words, the portion of audible hearing. And then we have diagnostic ultrasound and hypersonic ultrasound. And now to focus on the spectrum of sound, we have infrasound, sound, and ultrasound, where human hearing is located somewhere between 16 Hz and 16 kHz. Power ultrasound between 20 and 100 kHz, extended range ultrasound between 100 and 2 MHz, and then finally we have the portion that we use for diagnostic ultrasound between 2 and 10 MHz, which is the so-called high frequency ultrasound. Maybe it's easier to appreciate where ultrasound is if you look at this diagram. We have the bumblebee at 150 Hz, the middle C at 256 Hz. Here's the mosquito and the grasshopper. So if you went to discos and you damaged your hearing, you will not hear grasshoppers anymore. Here are the bats. And then finally, somewhere in the range of 3 MHz maybe, is the diagnostic ultrasound. But how does one create ultrasound waves in the first place? Well, with the help of so-called piezoelectric crystals. These crystals have a special property. If we apply an alternating current, then they start to resonate. They start to swing, and thereby they emit an ultrasound wave. By changing the frequency of the current that is applied, we can also change the frequency of the ultrasound beams which are emitted. But these crystals also have another very important property. If they are hit by an ultrasound beam, they begin to swing, begin to resonate, and that can be converted into an electrical current, which can be recorded. So the crystal fulfills all the criteria we expect. It can send an ultrasound wave, and it can receive an ultrasound wave. Have you ever asked yourself what is inside a transducer? Well, I can tell you. A lot of very thin wires and cables which are attached to the transducer elements which are somewhere up here. You have some dampening up here for the crystals, and then you have all sorts of other electronic elements which, honestly, I don't even know what they are. But keep this in mind when you have these transducers in your hand, because if you drop them and if they break, they're very expensive. We have seen incredible developments in transducer technology in the last 2 or 3 decades. We can not only put these transducers into transesophageal probes, but even into catheters and perform intracardiac ultrasound. We're now also able to use 4D imaging technologies where we don't only image a sector, but a whole pyramidal volume. We can even perform what we call live 3D imaging. I am sure that this is not the end of the story. And on the horizon, we can see a completely new transducer technology evolving, the so-called silicon transducer technology. Just to give you a better feeling of what this could maybe offer to us in the future, just a few slides would show you what the advantages are. We have higher bandwidth, we can use much more elements. We can steer the ultrasound wave much better. And we can, which is very important, perform the processing within the sensor. Such transducer chips would be produced very similar to the way that we produce chips for the computer industry. To give you a better understanding what the full potential of such a transducer would be, here is an example of a conventional transducer where normal piezoelectric crystals are used. Now, we have to attach cables to these crystals, cables which bring the electric currency to the crystals and which receive the signal and then bring it to the place where the signal is processed. Now, this is very difficult to do, and the size of the cables kind of limits the amount of crystals we can put in here. This is not the case if we use the silicon technology. Now, everything, the whole processing would be here, right here at the tip of the transducer or in the transducer. And only one cable would then record or bring the processed information to the machine. So in this way, we could use much more elements, and thereby also increase the image quality. The ultrasound wave has an effect on the tissue. We talked earlier that we are causing compression and decompression, and therefore the ultrasound wave must also be described with respect to its acoustic power, its intensity, and the mechanical index. Now, what are these things? The acoustic power is the amount of energy which is produced per unit time. Energy is measured in joules, and watts, therefore, is joules per second, in other words, the unit with which we describe acoustic power. The intensity is related to the acoustic power and simply describes the concentration of energy on a certain spot. In other words, how much energy per square centimeters, for example. So, the unit is watt per centimeter square. And why are these factors of concern in the first place? Well, simply because ultrasound should be safe. And we know that ultrasound causes bioeffects, and that these bioeffects depend on the intensity of exposure. We can note thermal effects and also cavitations, little explosions, gas explosions which occur within the blood. You'll hear more about cavitations when we talk about prosthetic valve disease. But you can be reassured that ultrasound is safe. There are no reports of adverse effects. Still, we should try to keep the mechanical index and the output factors as low as possible, especially in fetal imaging. Now let me come back to an issue which we discussed earlier: penetration. Remember, we said that as the ultrasound wave passes into the body, into the tissue, it gets weaker and weaker. And sooner or later, we do not have enough energy to really create an image. Now, penetration not only depends on how much ultrasound waves are reflected or scattered, it also depends on the ultrasound frequency we use. And this is very important. Remember, the higher the image frequency is, the less penetration we get. Now you might ask, why should we use high image frequencies in the first place? Well, because there's a trade-off. If we use low frequencies, we have poor resolution. So you can choose either you have good resolution and poor penetration, or vice versa. What does that mean for us? Well, we have to choose the imaging frequency depending on the patient and depending on which organ and what we want to image. For example, if you have a very slim patient, you will use an image frequency which is very high. Then you have a very good resolution and you do not need such penetration. And if you have an obese patient, you'll aim for a good penetration and thereby use a low frequency transducer. I know this is a lot of information, but you can always go back to the fact sheets and look up these things. But before I conclude, I just want to mention one last thing which is also very important. Ultrasound wave is not emitted constantly, but in form of pulses. Why is that so? Well, simply because that allows us to determine how long a wave travels. We have to know which wave belongs to which wave. And as you will see later in this chapter, it's very important also how long these pulses are and how high the pulse repetition period is. In other words, the interval from one pulse to the other. This will also be an important determinant of image quality. So this concludes the first part of this chapter, the physics of ultrasound. There's a lot of information in this chapter, I agree, but I will review this information way at the end of this lecture, or at the end of this chapter actually, in the summary section. And don't forget, you can also go to the fact sheets where the most important issues are also mentioned.